Well, hello everyone, NNNI here, and I know it's been quite a while since I uploaded any sort of video, but then again I haven't been doing anything practical for the past 2 months since I don't have an oscilloscope, which I'm waiting for right now. And a disclaimer before I start this video, all my regular kind of subscribers, for God's sake, go hit the like button and get out of here, because this is going to be an extremely long and boring theory video. And theory is something which most people, most don't like. So I'll give you 5 seconds to complete the task. Done. So I hope you hit the like button and have run away somewhere. So this is a problem that I encountered in theory while doing a few calculations. This was something I realized. To understand this problem further, for those viewers who have persisted so far, I'm going to be telling you about inductance. So what we have here is basically a coil of copper wire, and we have a voltage across the copper wire, and we have a current I flowing through it. I hope I'm not drawing too small. This is my first teaching video, so don't bother. And obviously you have a loop of wire and a current flowing through it. What do you have? Of course, a magnetic field. And what does a magnetic field produce? Current. And according to Lenz's law, the current produced by this magnetic field is in the opposite direction to the current that enters the inductor. So what do you have? This thing is called inductive impedance, and if I'm right. And the current time graph looks something like this. Current on the y-axis, time always on the x-axis. So you have a linear rise in current, perfectly linear, depending on the voltage across these two terminals, and that's given by the relation V by L is equal to di by dt. So that's pretty much it. So if you have an increase in voltage, you have an increase in current for the same amount of time, and less inductance means more current for the same voltage and time. That's what you can deduce. So well, let's look at this problem in more detail. I am going to rewrite the formula. V by L is equal to di by dt. And my 3S LiPo. The fully charged voltage is 12.6 volts, the nominal voltage is 11.1 volts, and the fully drained voltage is around 9.6 volts if you take 3.2 volt per cell as dead for safety. But nominally it's 3.0 volts. We won't bother with that. And let's look at the current time graph for these three voltages. Let me take the inductance of my primary side to be 10 microH, and my current value, the current at which I want to stop, 5 amps. So I want to represent 5 amps by the dotted line over here. So let's start off with 12.6 volts. Since the voltage is high, the current will also be high for the same time period in inductance. The current rise time, that is the gradient of the slope. So the current rise will look something like this, and it's going to hit 5 amps at time t, t1. I hope that looks like a T, not a cup of tea, T. And now at 11.1 volts, the current rise is going to be a bit slower, and it reaches 5 amps at T2. And at fully drained, the current rise is even slower than that, and to reach 5 amps it takes time 3. So you can see the big difference in the time depending on the state of your battery, and now that creates problems. So let's say you have a PWM source, for example a 555 that creates a square wave with a set time period. Highlight the word set over here. So dt is constant, your inductance is constant, and your voltage is changing, and so is your current. So for example, you have calibrated this time period at 11.1 volts, which is the mistake I made. So at 11.1 volts, the current can rise up till the set voltage, in this case 5 amps. But what happens when your voltage drops or you're using a fully charged battery, obviously the current is going to rise faster. So when the battery voltage is full, you have a faster rise in current. So for the same switching time period, you get more current into the primary coil than you originally intended to. And the opposite thing with the fully drained state. The current rise is extremely slow. So you have a current less than the current that you desired, or rather calculated at 11.1 volts. And this is the problem I've been trying to solve. Now, how do you solve this type of problem? The easiest and simplest method, which I will show you right now, involves this a current shunt resistor of a very low value, 0.10 ohms in series with the MOSFET and the primary winding. Oh god, why do I keep drawing off-ramps? And this is the controller. Let's keep it as C. And you have this input over here. This is the secondary winding. This could just be a simple op-amp circuit if you know how to wire that up. So this is basically the simplest current controlling circuit. So you have a current flowing through here, and that produces a voltage across this resistor, since V is equal to IR, directly proportional to the current flowing through it. So if you want 5 amps, you just have to plug it in. V is equal to 5 into 1 by 10, that will give you 0.5 volts. So when the voltage across this resistor exceeds 0.5 volts, you know that it's at 5 amps, and this controller can turn the MOSFET off. And now the current drops below 5 amps and it can turn on again, and it's a feedback loop basically, and it continues doing this. But what if you don't have space for this current shunt resistor? It's very difficult to get small resistors of such low value. Now the solution I came up with, sorry guys, involves a bit of programming. So we have the same circuit, practically everything is the same over here, except that I have eliminated the current shunt resistor, so the MOSFET is tied directly to ground. Secondary winding, and this is your power supply. Yes. So what I'm doing is I am setting up a voltage divider, 5x voltage divider. I'll tell you why later. 4K, and that becomes 1K. So you have a 5 times voltage divider feeding into this controller that controls the MOSFET. And as you know, the current rise depends only on the voltage and inductance, nothing else. So we don't need a resistor here to measure the current. If we know the input voltage and if we know the inductance and we program the current that we want through the primary side, we can easily calculate dt. Simple algebra, you know 3 things, you can find out the third. So by rearranging this equation, you get time is equal to inductance into change in current by voltage. So you know the inductance, you program the current, and the voltage is sensed, and you have dt. So you can just produce a PWM wave depending on the dt value. Now you could just simply do this if you are using an Arduino. This is a bad method. So you first turn the PWM signal on, you set up a delay dt depending on the value calculated here, dt, and you digital right PWM low. So you turn the PWM off, and then you can have an arbitrary delay. And now over here, microseconds or whatever you've programmed your Arduino to do. So this is basically how my solution works. I don't think I'll be posting the full code until I test it with an oscilloscope, and that is key. But my capacitor charger is going to be revolutionary. Keep that in mind. It's going to revolutionize. fine, it's going to change stuff.